All right, so our next speaker is Markus Dierigl, and he's going to be talking about string universality and mixed anomalies. So please, Markus, the floor is yours.
Yeah, thank you very much, and a great thank you to the organizers for putting together this workshop. So since the organizers asked me to be on topic, sort of, I decided to give like a summary of the work I did during the last 3 years or so in the connection with string universality. And of course I have many collaborators, many of them are here, so feel free to approach them during the coffee breaks and ask them. Okay, so I list some of the works that I will mention in this talk here on this slide. So let me start by saying what happens if I have a theory that is gravitational and contains a p-form field, right? It's very common for us because we work with supergravity that have these fields naturally. In string theory, they're everywhere, right? Raman fields and so on and so forth. You just have this, this action here, which is a kinetic term, but this action turns out to generate some generalized global symmetries, right? So if you have a p-form field, you get two global symmetries. You get the electric one, which is just shifting this p-form field by a flat p-form. And you get the magnetic dual symmetry, which is a q-form symmetry, where q is d minus p minus 2, which shifts the magnetic dual as such. But then, of course, there's a problem, because I just told you you're in a gravitational setup. I told you this theory would have global symmetries, and there are no global symmetries in quantum gravity. So if you claim that something like this appears, you better get rid of them until you hit the point of the UV completion. So how do we do that? Well, the natural thing you would do is you would break them, right? And you break them by just coupling your p-form fields to dynamically charged objects. And since they're higher form fields, the electrically charged and magnetically charged objects are generically extended. So for the example I pointed out above, the p-form field would couple in this standard fashion to a p-dimensional object, and the magnetic q-form couples to this q-dimensional object. Right? But you have to be very careful, because you have to include enough of these states in order to break everything. So there is no even discrete subgroup left, which would again lead to global symmetries and would spoil your no global symmetries conjecture. So how do I do that? Well, I also have to be careful in the other direction. If I break them, I shouldn't break too much, because I will end up with a theory that has inconsistencies due to Dirac quantization, right? So imagine I have a magnetic object that I call minimal, that generates in its asymptotic geometry, it generates this magnetic flux on a p+1 sphere, right? So this is the magnetic object, so I draw it as a point, but it can be extended, and it has this sphere around it, which is threaded by this magnetic flux. So now how can I prove, or how can I show that I have to be careful in terms of Dirac quantization? Well, I can take the associated electric object and put it on a p-dimensional submanifold of this asymptotic sphere in such a way, right? And then say, is this configuration consistent? Right? And the answer is, well, it depends on the charge, electric charge of this object, because I can use Stokes' theorem, and I can either fill this electric coupling of this p-dimensional object in the interior, so then I have a picture like this. But I can also use Stokes on the outside, and I do the following thing, and the demand that is consistent means that this gauge invariant quantity has to be single valued. And for a minimal magnetic charge that I normalize in such a way, that would tell me that the electric charge has to be integer, right? So in particular, if I would now include something that is not integer, I run into a problem. It's just an inconsistent configuration. So whenever you want to get rid of these global symmetries, you have to be careful. Now this is actually correlated with something that is a large gauge transformation, and the way this is true is just simply how we construct this higher form magnetic fluxes is we take this p+1 dimensional sphere, we cut it in the middle, the equator is a p-dimensional sphere, right, and we glue them together up to a large gauge transformation. So this statement of Dirac quantization is sort of a statement that this electric operator here, this higher dimensional generalization of a Wilson line operator, is invariant under this type of large gauge transformation. Okay, so if it's not, then it points to your theory not being gauge invariant, so you can call it an anomaly in this sense. Okay, So how do I break it correctly? To summarize, right? I have this electric states, I have this magnetic states, and I just should include all, as many as possible, but not too many, right? So this is the correct picture. I have this lattice, and I should include all of them I'm allowed to, but I should not have these free columns or rows, because then I would generate like electric or magnetic remnant discrete symmetries. But I should also not include too many of them, because I would violate Dirac quantization. Okay, so that's the general story that we'll work with for the rest of at least of the first part of the talk. Now the thing is that not only these objects are included, the elementary object are charged, but also other things can be charged, right? So, for example, I can have a gauge sector, which has the standard two-form field strength, which can carry electric charge. So if you have a coupling in your theory of this type, this tells you that this gauge configuration generates an electric charge under the p-form field. The same is true for the tangent bundle. So if I have a coupling of Cp to some combination of the curvature two-form, that means my space-time manifold, if it has curvature or gravitational instanton and the likes, can carry these electric charges. And also if I have other p-form or k-form fields that couple in such a way, right, they will also generate these charges. And all of these configurations need to satisfy the same quantization condition. So I should never have the possibility to generate something that is fractional in order to violate the Dirac quantization. And that's sort of how we get extra constraints, and we can approach some aspect of string universality. So this issue is a little bit subtle, because usually it's related to not only local information of my gauge theory or my gravitational theory, but something that I would call global information, right? So it's something, I have this topological term that usually is integer quantized. So let's take the example of a gauge sector where I have this instanton density trace f squared. And whenever I have a simply connected non-abelian gauge theory, the instantons would be, the instanton numbers are integers. Now, however, if my gauge theory is not simply connected, but you have this, for example, SU3 mod Z3 or other situation, then in general it can be fractionally charged, right? So it really depends on this global piece of information. So if it's a pure gauge theory, I would never be able to test it in local scattering experiments, because I have gluons, right? Only, so these are the same local degrees of freedom here as they are here, but it has to do with this global properties of my theory. The same is true with the gravitational side, right? So there I can have gravitational instantons. So because slide is not wide enough, I, instead of trace r squared, I just wrote the first Pontryagin density, right? So it is also typically integer quantized in the correct units, right? But only depending on the type of manifold you consider. So spin manifolds will have a different quantization law than, for example, spin C manifolds or other type of manifolds that you would allow. So again, it depends really on the global structure of your space-time manifold and what kind of the quantization conditions appear here. And of course, this leads to a correlation with the Dirac quantization whenever I now couple my higher form fields to these topological densities. So today I will mainly focus on the gauge sector, but I think there's a lot to be discussed also for the gravitational sector, actually. So now let me give a little bit more explanation on what this global data means. So I already said that if you have a pure non-abelian gauge theory in any dimension, right, your local degrees of freedom are gluons, and there will be the same for all theories that have the same gauge algebra. But we care about the gauge group, not only the algebra. So that means that we care, or we have to focus on this center of my non-abelian group. So SUN, for example, has center ZN, but also spin groups and other groups have a discrete center. Now, if you have a pure non-abelian algebra, then you have a center one-form symmetry. Also, again, a global symmetry that would appear, and of course in quantum gravity, you would not allow global symmetry, so again, you have to get rid of it. And there's two ways here. So you break it, that's the same as we did before, right? We include now dynamical states that are charged under the center. You get rid of the one-form symmetry. For example, in the SUN case, if you have a dynamical degree of freedom in the fundamental, you would break the ZN one-form symmetry completely and you're fine. But you can also gauge it, and by gauging the center symmetry, you go from the simply connected version to the non-simply connected version. But you have to be very careful, because by that you include these fractional instantons that can change your conclusions about Dirac quantization. Right, so that's the argument we're going to run here. And also in this gauged version, of course, you're not supposed to have some representations that are charged under this as part of the center that you gauged with. So it really has some restrictions on the spectrum of dynamical fields of your theory. So for example, if you have a theory that has gauge group SU3 times SU3, it can have representations of the form like fundamental times singlet, whereas if you have SU3 times SU3 mod Z3, this cannot happen anymore. So I imply that this Z3 embeds non-trivially in the center of both groups, right? And depending on how you embed it, you either have fundamental, fundamental, or fundamental, anti-fundamental. But this representation could never show up. Of course, there's a subtlety here. Once I do this gauging, I get this quantum symmetry, the dual symmetry on the magnetic side, and I also have to include some magnetic states here. But let me not go into detail. So what are some examples? Well, in 4 dimensions, I can just take like an axion degree of freedom, a periodic scalar field that couples to my instanton density, right, of this type. And there have been some analysis precisely of this mixed anomaly that I want to discuss between now a shift symmetry of the axion and this gauging of the one-form symmetry in the gauge sector here. And in fact, there has been a couple of recent papers where they do precisely this realization in the standard model. And you might be surprised or you might not, depending on whether you've heard about it, that we actually don't know the gauge group of the standard model. We know the gauge algebra, but precisely this global realization, there could be a Z2 discrete factor in the embedding in the center, a Z3 or a Z6. Right, and depending on what it is, actually this coupling will be restricted, and that actually has consequences for axion physics, under some assumption, of course, that there is a single axion, that is the QCD axion, and so on and so forth. Okay? But of course, these couplings are very general. So for example, if you go to 6 dimensions, n equals 1,0, you have a bunch of tensor fields. So you have these 2 forms that couple to the instanton density. Right, and there's much work going on here. But today I will actually focus on the 8-dimensional case, minimal supersymmetric, so 16 supercharges. And the reason is that in this case you have a single 4 form that is in the gravity multiplet that couples now to all the potential gauge sectors you have in this universal way. So you have C4, wedge, some coefficient that I will explain, and then these instanton densities. And that is the reason why in 8 dimensions, because this is the unique term that universally couples, you get the strongest constraints. You can run similar arguments as we did for 6D, but because you have more flexibility, the constraints are not as strong. Okay, so what is the logic here? Well, we start with this term here, right? Then we do a large gauge transformation of the C4. Remember, this is the thing that embeds, or this code encodes the Dirac quantization. And then we better make sure that this thing I get here integrates to an integer, right? And that means because I normalize the instanton density in the appropriate way, and this is also in integer cohomology, that the sum over all these coefficients that appear should be an integer. Then I'm fine. I don't have this mixed anomaly between the global one-form symmetry of the gauge sector and this large gauge transformation of my p-form field. And now, if I, on top of that, include some other restrictions that I can get, for example, from anomaly inflow, and I apologize that I should also include the paper by Huri here. So the consistency conditions in 8 dimensions with n equals 1 supersymmetry tell you that the rank of your gauge group should be smaller or equal than 18. And as we heard from Miguel, by using these anomaly inflows and I-folds that are predicted by the cobordism conjecture, you can also show that R minus 2 is divisible by 8. So this gives 3 possibilities, 18, 10, and 2. So what are these coefficients that need to add up to an integer? Well, if you have a gauge group that is composed out of non-abelian factors with some discrete quotient. Again, I embed this in all this simply connected pieces here. Then it's composed out of three things. Namely, there's a Qi, which is precisely how fractional can my instantons be, right? There is some Ki squared, which is how do I embed my Zn into the different simply connected factors. And then there is some discrete redundancy in the supergravity theory in principle, which is related to integer levels. However, one can show from anomaly inflow arguments that at least in the case of rank 18, all of them have to be set equal to 1. So in the rank 18, you don't have this redundancy here. And then you can just run the argument, right? So let's consider we have a rank 18 theory in 8 dimensions, n equals 1 supersymmetry, and it only has SUN gauge algebra factors. And then you just are faced with a challenge of combining. So the Q's take this form here. And now you have to find a combination such that the rank adds up to 18, and this number is given by an integer. And it turns out to be very, very restrictive. And of course, we run the program and showed you what kind of theories are consistent. And I want to point out there's really a very strong bottom-up constraint. So I only gave you the supergravity and anomaly arguments. There was no string theory involved here. But of course, 8D, n equals 1 supergravity, there's a lot of string theory constructions, and we heard that one of the best explored maybe is F theory on elliptically fibered K3. So you can ask the question, well, I found this anomaly constraint. Can I discover it in string theory as well? And it turns out that actually if you go to the mathematics literature, you will find that if you have elliptically fibered K3, where all of the Kodaira singularities that you have are of A type, so that's the SUN gauge groups, you get a geometrical condition. So if you're familiar with F theory, this has to do with the geometry of torsional sections. And it reads as follows. And you see that's precisely the same as here. So actually the anomaly constraints that you find in supergravity, just as like a consistency constraint of your gravitational theory, is actually ingrained in the compactification geometry of F theory. Right, so I think that's very astonishing, meaning that we have a reinterpretation of some of these low energy consistency constraints in terms of a compactification geometry. Now, of course, as Miguel also mentioned, there is many string constructions of these theories. One of them has been investigated in very great detail and in the huge complete list of these models by many people here in heterotic string on T2 with Wilson lines, and you have to be careful. And there, to find the gauge group, it's really about this lattice embedding into some string lattice that can be Narayan or CHL and whatnot. With Miriam Cvetic, Ling Lin, and Hao Shang, we did a similar construction where we don't do the heterotic string, but we construct, in principle, these lattices from string junctions in type 2b. So you really have this PQ branes, and then you can make sure that they have to end somewhere, and by this restriction that every PQ string has to end because you're in a compact geometry, you can find precisely the same embedding constraints, which is quite nice. So this is now, of course, a very strong top-down construction. So to summarize the first part, let me mention that anomalies are very powerful to constrain models from bottom up, and they can be matched from top down, and sometimes there is a beautiful relation between the two consistency conditions, right? So in particular, sometimes you can find the hints on what the geometry of the compactification should be. And I want to stress here that SUSY is not needed because I talked about anomalies, so those are topological. I don't care about SUSY, but of course, in the end, I do because the SUSY restricts the spectrum a lot. So I don't have to check everything, but I have a single 4-form in AD, right? So that is a lot of restriction entering there. And maybe as like it's like a motivation, I think if we now start including all generalized symmetries, also the gravitational sector, I think there is still a lot to be discovered in this area. Now, as always, even though this is very powerful, there's a flip side of the coin. Right? So maybe string theory is not as unique as we might think. So what do I mean by that? Well, think of a theory that actually has a very subtle type of anomaly, a discrete kind of anomaly. So that means there is no real modification of the local degrees of freedom. It's very subtle, and we want to get rid of it. And there's various ways how we can get rid of it, so that we can, for example, try to embed some of the gauge groups in a larger group such that the anomaly vanishes. I can have some topological version of the Green-Schwarz mechanism, meaning that I don't include new dynamical degrees of freedom, only topological ones. So I don't modify the local dynamics. Or I can do a discrete modification of the fields I already have in the theory. So again, you wouldn't see it by local interactions, but only by subtle modifications. And in principle, how I cancel the anomaly is actually not unique. And that is precisely what my comment was for Severin's question. So turns out in type 2b string theory, duality symmetry in 10D, I'm talking in 10D here, the duality is anomalous. And you want to cancel this anomaly. But there's different versions, so we explored this in this paper with Jonathan, Arne, and Miguel. There's different versions how you can cancel this anomaly, namely, for example, by this discrete modification of the Bianchi identity of the self-dual phi-form field. You can interpret this as the minimal version, because you don't include any new fields, not even discrete ones. But you can also include new topological sectors, right, of this BF type that, for example, have discrete higher form fields. And they can also do the job. And I don't know of any argument that either this or this should be forbidden. So if both of them are allowed, this leads to this picture that also was on Miguel's slides, where instead of this various asymptotic limits, you now also split these different limits according to the various UV completions associated to different topological sectors. Similar things happen in 6 dimensions. So in a paper with Paul Oehlmann and Thorsten Schimanek, we explored discrete gauge symmetries in 6D. So again, discrete gauge symmetries, they only have this very subtle anomalies, right? So this is the very discrete things that doesn't really change the local interactions. And you might ask the question, well, in 6D, usually if I ask a supergravity person, like, how do I classify my theory? Well, you tell me the number of tensor multiplets, you tell me the number of neutral hypers, or hypermultiplets, the charges, the vector multiplets. So here we have a model that only has a Z3 gauge, so there's no vector multiplet, right? It's not a dynamical degree of freedom. We have the same number of neutral hypers, we have the same number of charged hypers, and the same number of tensors, but different F-theory geometries. You know, it's like, okay, is this the same theory? And it turns out, no, it isn't, because the anomaly that appears in this Z3 is actually cancelled in a different way, and that's precisely this discrete ambiguity that can happen in these kind of theories. And because in this case we rely on supersymmetry, or we have this supersymmetric model in terms of F-theory compactification, you can actually test this really by topological string partition function approaches. So you can test that the anomaly inflow on strings also for discrete theories, right, is different, and it's both is realized. And yeah, so let me give you the second lesson that you should take home. So anomalies and the cancellation, they're very powerful, but they also have this room for ambiguities sometimes. And of course you can ask the question now, are some of them forbidden? If yes, why? So this would lead to some discrete swampland constraints, and these discrete swampland constraints are often very, very tricky. So it's like with the gravity conjecture and the sublattice, you can often make this, or there's no good argument excluding that you make the sublattice arbitrarily large, right? And this has to do with some discrete data. Can we make progress there? Or if they are allowed, do we really face now the issue of a string landscape that has this discrete possibilities? Both of them are exciting. Okay, so as a summary, let me just flash these 2 lessons you should learn, and let me mention that, of course, we now spend a lot of time in the landscape and deconstructing and constructing the landscape in Landscapia, but you should be very careful, because if you're in the landscape, the swamp thing is never very far from you, and in fact it's true for Landscapia, because Swamplandia is also not very far from you. And so it's a pleasure to announce that it will happen in this beautiful place, as you can say, very dangerous, right? There's the landscape, and you're basically surrounded by the swampland. in this monastery Seon close to Munich, end of May, back to strings and geometry. So if you want to travel a little bit in Germany, this is a great opportunity, I would say, to attend both of these conferences. And with that, I end my talk, and of course, feel free to ask questions. Thank you very much.
Right, Markus, thanks a lot for the very nice talk. Questions? Yeah, there's a few there. Timo was first, I think.
This 60 example with the Z3, with the same Marshalls spectra, how exactly do the F-theory geometries differ? Can you remind me?
So I can tell you from the field theory side, what differs is how the anomaly the anomalies on the strings coupling to the tensor multiplet and the gravity multiplet. In one case, so there you have three possibilities. 0 is not allowed because you need some anomaly inflow in order to make this work. And then you have 1 and 2, right? And these are precisely how these models differ. So they have the same spectrum, they cancel the same anomaly, but you can cancel them in two different ways, which you can extract from the anomaly inflow onto the strings in this model. And that is different.
But what's the geometry? Same manifold? Different
no, it's a different manifold. It's a different manifold. I can tell you.
Different model while or what?
I think I have to check the table. Probably it's the Euler number. That might be but it's no, the neutral hypers are the same. So I can check the table, but we have this list.
There was a question here first. Here, yeah. And then.
So you said that one way of curing the type 2b duality anomalies would be to modify the Bianchi of F5 by some discrete terms. Could you be more specific?
Yeah, I could. So, right. So the duality is SL to Z or some refinement thereof, like MP to Z, and there is a way to decompose it into a Z3 and a Z4. So this is amalgamation is the phrase, right? So there's a nice way to encode the duality bundle in a Z3 bundle and a Z4 bundle. And this topological term will precisely be a cup product of the characteristic classes of this discrete gauge bundle. So it will, these are classified by H1 of BZ3, BZ4. So this gives you the characteristic classes like the Chern class for U1. But they're discrete, right? They are only Z3, Z4, Z9, Z3 or Z4 valued, and you cup them and include them in there. So there is really no modification for any continuous variation, but only this very discrete thing, which makes it so hard to detect, and that's why it hasn't been in any calculation.
One last question.
Just my absence of knowledge of Calabi-Yau force. So when you compactify, for example, M theory and Calabi-Yau 4, you get some anomaly, which is the Euler characteristic divided by 24. Are all the possible Calabi-Yau force having an Euler characteristic which is a multiple of 24, or what you're saying is that you cannot compactify unless.
So there is some restrictions. So Calabi-Yaus as spin manifolds usually have a coarse-grained integration, for example, of the second Pontryagin class, and the same here, right? So for example, if you restrict to spin manifolds, so these are usually classified in this deformation classes. In 4 dimensions, spin manifolds are generated by K3. That has the lowest number, which is the 1 over 48 P1 is equal to 1. But of course, we know that we can take type 2b and put it on a CP2, right? Which is not spin, but we can compensate in F theory by putting some non-trivial duality bundle. And then you can get around these consistency constraints. And a similar story I could imagine happens for Calabi-Yau 4.
All right. Then if there are no further questions, now we will go for the coffee break, and then we have a talk and another discussion session. So let's try to reconvene here in about 20 minutes or so. But first, let's thank Markus again.